In this video, we're going to review a few things in the characteristic properties unit for your test. You do have a checklist for the unit, so be sure that you are looking over the checklist and that you are familiar with everything on that. One of the items on the checklist refers to density problems, density calculations. It's one item on the checklist, but we know that it makes up a very large portion of the test. In this video, we're going to look at some density calculations as well as some things with apparent mass, and we'll look at a cooling curve at the end. Before we jump in, the unit is called characteristic properties. Without looking at your notes, are you able to define that right now? Pause the video and try it yourself. If you said that a characteristic property is a property which can be used to identify a substance, one that is unique to that substance, there's more than one way to say that, one that can be used to distinguish one substance from another, that's another way you could say it, that's fine. But there's another part to the definition. It does not depend on the amount of substance present. So be sure you've got both parts to the definition. You can use a characteristic property to identify a substance. The characteristic property does not depend on the amount of substance present. What are some characteristic properties? Can you list a few that we studied in the labs? Freezing point, boiling point. Now, if you've already said freezing point, you wouldn't say melting point also. Those are the same things. You could also mention sublimation point if you wanted. That's not one that we saw in the lab, but that would also be possible. You might say density. That would be another characteristic property as well. Those are ones that we've studied in our experiments in this unit. All right, let's jump in here. If you've got your science booklet, you'll need to refer at some point to this, the page 116, the back of your solubility chart, densities of common substances. Question number 1, we've got a sphere with diameter 6.00 centimeters and a mass of 22.5 grams. What's the density of the sphere? See if you can pause the video and do this yourself on a piece of paper with a calculator. In your answer, it's not just getting the final answer that matters, it's how you set up and do your work, right? The first thing I want to see is always a formula, so we're finding volume of a sphere, so I want to see that formula, 4/3 pi r cubed. Now the diameter here was 6.00 centimeters, which means the radius is 1/2 the diameter, so 1/2 of 6.00 centimeters would be 3.00 centimeters. There's the radius, so be sure you've shown that. So now we can say 4/3 times pi times the radius, 3.00 centimeters cubed. And now I'm just going to grab a calculator to evaluate that. 4 times 3.14 times 3 to the power of 3, and then divide by 3 at the end. So I get a volume of 113, and I'm going to keep 3 significant digits because of that 3 digits that were in the original diameter and radius. So 113 cubic centimeters is the volume of the sphere. When we're finding density, which is what this problem is asking for, this is the only density problem where I want to see the density formula used. D equals m over v. We know the mass is 22.5 grams, and we know that its volume is 113 cubic centimeters, so this is going to have a pretty small density. So 22.5 divided by 113, and on a calculator we can see 3 digits on top, 3 digits on the bottom, so from my calculator 0.199, I'm going to keep 3 digits, grams per cubic centimeter is the density of this spherical object. Question number 2, we're going to need the density of mercury to do this problem. Pause the video and see if you can try this one on your own. So the student needs 10.00 grams of mercury, but only has a graduated cylinder to measure that mercury. The question is, what volume of mercury should be used? So we're going to need the density of mercury from our book. The density of the mercury, I'll just look it up here, is 13.58 grams per milliliter. And the question is, what volume of mercury would have a mass of 10 grams? So we're not going to use the density formula for this. We're going to use a unit multiplier. So we take the 10.00 grams of mercury, and with one unit multiplier, we're going to get rid of the grams and ask how many milliliters, what volume is needed. When we see a unit multiplier with grams and milliliters, we know we're looking at density. The density was 13.58 grams, so the 13.58 goes beside the grams in my unit multiplier per milliliter, so 1 milliliter will be on top. With my calculator, this will mean 10 divided by 13.58. The 13.58 is on the bottom of the multiplier, you divide by it. If it's on the top, you multiply by it. So with the calculator, 10 divided by 13.58, now 10 had 4 significant digits, 10.00, and 13.58 has 4 significant digits, so I need to keep 4 digits in my answer. So I'm going to need 0.7364 milliliters of mercury to get 10.00 grams. So less than 1 milliliter of the mercury will weigh 10 grams. You can get a sense of how dense that actually is. The third question, pause the video here and see if you can do this. We're going to need to, looks like we're going to need to find the density of glycerin on the back of your solubility chart. I'll just quickly write that here. The density is 1.26 grams per milliliter. So this question is sort of the opposite of the one we just did. We're given a volume, 4.00 liters of glycerin, and the question is, what mass of glycerin is that? Now, because we're given liters and not milliliters, the first thing I'm going to do is just switch liters into milliliters. Now I can do a density calculation. I can get rid of those milliliters and switch to grams. And again, when I see grams and milliliters in a unit multiplier, I know I'm looking at density. So the first multiplier here is just the conversion of milliliters to liters, and everybody should know that there's 1,000 milliliters in a liter. You don't want to make a silly mistake with that on a test. The second unit multiplier is our density, 1.26 grams, so 1.26 goes beside grams, per milliliter, so for every 1 milliliter. Now with my calculator, I'll be multiplying 4.00 multiplied by 1,000 multiplied by 1.26, because those numbers are on top of the unit multipliers. So 4 times 1,000 times 1.26, that's going to give me on my calculator 5,040 grams, right? The liters canceled out, the milliliters canceled out, and we're left with grams as our unit, which makes sense. We're looking for mass. And we needed to have only 3 digits, right? 4.00 has 3 significant digits, and our density, 1.26, had 3 significant digits. We don't use the number 1,000 because it's an exact number. It's not a measurement. There's exactly 1,000 mils in a liter. The other 2 numbers are measurements. So because they each have 3 significant digits, we can only keep 3 significant digits in this answer, which means we need to convert this to scientific notation, and we'll write it as 5.04 times 10 to the power of 3 grams. So switch to scientific notation, we can show 5.04, which has 3 significant digits. Now on a test, if you left 5,040 as your answer, you'd still receive full marks because you remember I allow plus or minus 1 significant digit on most problems. Question number 4. Pause the video here and see if you can try this one on your own. So we have a 65.0 gram rock. It's being dropped into methanol in a graduated cylinder, and it sinks to causing the level of methanol to rise from 22.3 to 47.6. We're going to need to answer, is the rock more or less dense than methanol? How do you know? Well, I suppose we could calculate the density of the rock since we know its mass, and we can see that after sinking the volume rose from 22.3 to 47.6. We can see the volume by difference. Then we could look up the volume of the density of methanol and compare them. But a much faster way to do that would be to just notice that the rock sinks. If the rock sinks, then it must be more dense than the methanol. So since the rock sinks, it is more dense than methanol. And that's really all we needed to say here. Now the second part of the question is a little more complicated. What's the apparent mass of the rock in the methanol? Now we do have on the back of our solubility chart a formula for finding apparent mass. We know that when you put an object into a liquid, because of buoyancy, the object appears to weigh less than it does outside the liquid. It has an apparent mass that's smaller than its actual mass. Our formula says that the apparent mass is the actual mass of the object, in this case of the rock, minus the mass of liquid displaced by the object. Okay, so if I want to know the apparent mass of the rock, I need to know these two things. Well, the question above told us that the actual mass of the rock is 65.0 grams. That was its mass. So to find its apparent mass, we need to know this. What mass of liquid was displaced? Well, let's go down here and figure that out. What mass of liquid was displaced? Well, we know that it sank in the methanol, and it caused the methanol to rise, so we know the volume of methanol displaced. The volume of liquid, in this case methanol, displaced would be simply the final level, 47.6 milliliters, minus the initial level, 22.3 milliliters. Now, at the end of the day, I'm going to do this on a calculator so I don't make a silly mental math mistake. 47.6, take away 22.3, 25.3 milliliters of methanol was displaced. But I don't need the volume, I wanted to know the mass. So now I'm going to use the density of methanol, which I'll look up in my book, and I'll convert this volume to mass. So let's use a unit multiplier, 25.3 milliliters of methanol. We'll get rid of the milliliters and we'll ask how many grams is that. So now we need the density of methanol. It's not given in the question, so we'll look it up in our book. Its density is 0.79 grams, so 0.79 grams per milliliter. So with a calculator, 25.3 times 0.79 is 19.98, which will round it off will be 20.0 grams. So that's the mass of the methanol which was displaced. So up here we can say the actual mass of the rock was 65 grams and the mass of the liquid displaced was 20.0 grams, which means that in the methanol the rock would have an apparent mass of only 45.0 grams. So its mass is less, it appears to have a mass less than it did outside of the methanol. The last question on this quick review is involving a cooling curve. Pause and see if you can answer questions A, B, C, and D based on the cooling curve you see here. Its temperatures here on this graph are not in degrees Celsius like we're familiar with. They're in units that are called Kelvin, so their symbol here is K, but nonetheless they're just temperatures which you can read from the graph. Pause the video and try it yourself. So the question here tells us that the substance began as a gas and we cooled it. If we look at the 5 regions of this graph, A, B, C, D, E, we know that it starts off as a gas. So I'm going to write the word gas in that first region. And we're cooling the temperature of the gas down from about 450 Kelvin down to between 350 and 400 Kelvin, somewhere in there. This first plateau represents the first phase change, so we're going from a gas to a liquid. So in here we're going to have both gas and liquid present, and that's where the gas is condensing. If we were reading it the other way around, warming up, this is where the gas would be boiling. Sorry, the liquid would be boiling, turning to gas. We finished condensing here, and then as we continue to cool, the temperature drops again. So now we have just liquid present. And over here in region D, where there's another plateau, our liquid is now turning to solid. So we'd have liquid plus solid present, and that's where the freezing is occurring. Once it's finished freezing, the temperature would continue to drop, and we would have just a solid phase at the end. So those are the phases of the substance: gas, gas and liquid, liquid, liquid and solid, and then at the very end only solid. So the first part, what is the freezing point of the substance? Well, that's where the liquid is turning into a solid. So here we had liquid, here we have solid. This is where liquid is turning to solid. So we just have to move our plateau, extend it, extrapolate all the way over, and estimate what temperature that would be. It's between 250 and 300, and it looks to be approximately right in the middle. So I'm going to say that it's approximately 275 Kelvin. The boiling point of the substance is where the liquid turns to a gas, or the other way around, gas turns back to liquid would be the same temperature. So that's this plateau up here. If we read it backwards, liquid becomes gas. This is where you have both gas and liquid together. So there, the temperature at that plateau is a little bit more than halfway. So if this is 350 and 400, halfway would be 375. It's a little bit more than that. I'll estimate about 380, 385 Kelvin, something in that range. At what time did it begin to freeze? Well, if we were cooling, it begins freezing right here, okay, the beginning of region D. So that would be at 20 minutes. 20 minutes. It finished freezing right here, which would be at about 28 minutes, somewhere in there. Okay. At what phase was present? So solid, liquid, gas, or perhaps more than one phase at 15 minutes. Well, 15 minutes is right here, and so at 15 minutes we're in the liquid region, so this is only going to be liquid present. So there's a cooling curve of a substance from a gas all the way down to a solid state. We saw a boiling point here, a freezing melting point here, and we know the different phases present at each part of the curve. So that's not everything you need to know for your test, but it is a good overview of some of the things that are on the checklist for the characteristic properties test. This would also be a good thing to use as a review for your final exam of this unit as well. So good luck with your studying.